Hello friends, welcome to UGC EPG Pathshala. I am Dr. Dilip Kumar, Assistant Professor in Geography, Shahid Bhagat Singh Evening College, University of Delhi, New Delhi. The current session is on drainage mapping and morphometric analysis. Under this session, we will discuss on why it is important and the three aspects of morphometric analysis. The drainage mapping and morphometric analysis. Drainage is a system of draining water, passing of water over and through the land surface, ultimately toward the sea. The dictionary meaning of the drainage is a process of removing the gravitational water from soil using artificial or natural conditions, such that freely moving water can drain under gravity through or off soil. The area that collects water into the drain system with single outlet is known as drainage basin. It is an area that gather water from precipitation and deliver it to a large stream, a lake or an ocean, which is limited by a drainage divide and occupied by drainage network. The drainage basin consists of different types of pattern such as dendritic, rectangular, trellis and many more. The drainage system can be sequent or insequent. Sequent drainage system consists of consequent, subsequent, obsequent and resequent. According to the geological structure of the surface, the insequent drainage system has antecedent and superimposed type where there is a lack of adjustment to geological structure. The term morphometry is used in several disciplines to mean the measurement and analysis of form characteristics. In 1934, Emmanuel Martone defined morphometry in his book Trail de Geographique Physique as the numerical systemization and the form of the land relief as it can be interpreted from to topographic map. Basically, morphometry is the measurement and mathematical analysis of the configuration of the earth surface shape dimension of the land surface. It provides quantitative description of the basin geometry to understand initial slope or inequalities in the rock hardness, structure controls, recent diastrophism, geological and geomorphic history of drainage basin. According to Horton, drainage morphometry is a calculation of a range of dimensionless drainage network relationship based on a system of stream ordering, that is the numerical ranking of channel segments with a channel network. Drainage basin morphometry is measurement of the surface form of a drainage basin and of the arrangement and organization of the associated river network. The properties such as area, shape, gradient and relief are important element of form, while the stream network is investigated through a study of its component and of the way in which they are related. It enables us to understand the relationship among different aspects of the drainage pattern of the basin to make a comparative evaluation of different drainage basin developed in various geologic and climatic times. The mapping of drainage and their basin is most important for the development of land and water resource on a sustained basis and with constant increase in productivity is necessary for the sustainable development. These development depends on the prudent use of land and water resources, their conservation and development. In the face of enormity of degradation problems and constraint of resources, a scientific approach to land and water resources development and management calls for clear identification of critical area of treatment. Drainage basin is an ideal geophysical unit needed multidisciplinary approach to the land and water resource management for ensuring benefit on sustained basis. The characteristics of the drainage basin help to understand and model various natural processes occurring in the watershed, and these watersheds or hydrological units are considered more efficient and appropriate for necessary survey and investigation for assessment of these resources and subsequent planning and implementation of various development programs like soil and water conservation, command area development, erosion control in catchment, dry land or rainfed farming, reclamation of ravine lands, etc. The hydrologic units are equally important for the development of water resources through major, medium and minor storage project as well as farm level water harvesting structures. So, the watershed approach is more rational because land and water resource have optimum interaction and synergetic effect when developed on a watershed basis. Since the work cannot be started at the same time in all the watersheds due to management and resources constraint, a priority list has to be prepared. In this way, morphometric analysis of the drainage basin help us to prioritize the watershed on the basis of their characteristics. The prioritization of an area help in addressing the conservation effort to secure maximum benefit. The science of morphometry is concerned with the quantitative measurement and generalization of land surface geometry. The drainage basin and channel morphology are related to the geologic, climatic and hydrologic characteristics of the basin. Then it is necessary to describe the feature quantitatively in order to investigate these relationships. There are three aspects of drainage basin morphometry such as linear, aerial and relief aspect of the watershed characteristics. The number one is the linear aspect. The linear aspect of basin characteristics includes number of streams, stream order, basin parameter, basin length, bifurcation ratio, wandering ratio, overland flow and length of channel of all orders. Usefulness of ordering channel system lie on the hypothesis that basin size, channel dimension and stream order provide investigation is made for quite large number of watershed. Two basins have different linear measurement can be compared with respect to corresponding point in their geometry through the use of dimensionless order number. For reference, see the table number 1. Stream order. There are various systems of ordering the stream that are available. Stoller system, which has in fact slightly modified Horton system ordering system, was followed because of the simplicity. According the smallest unbranched stream segment was designated as a first order stream, the one formed by the merging of two such first order segment, the second order streams and so on. For example, there are 13 watersheds in the Sonkara-Nassau interflow named watershed 1 to watershed 13. In this ordering, the analysis reveals that the watershed number 1 is third order watershed, watershed number 2, 4 and 5 are fourth order watershed, watershed 1, 3 and 12 are fifth order watershed. Watershed 6, 8, 10, 11 and 13 are sixth order watershed and 7 is only one watershed is seventh order watershed. See the figure number 2, the stream number. The number of stream is calculated in each watershed after assigning the stream order in each stream. The analysis of the study reveals that the number of stream decreases as the stream order increases. There is more first order stream than any other order, and that the first order stream on the average are shorter and occupy a smaller drainage basin. The stream discharge increase systematically with stream order, and these relation indicates that the drainage network has developed in response to the erosive forces acting on erodible material that comprise the drainage basin. Bifurcation ratio. The bifurcation ratio as the index of relief and dissection, and it computed by dividing the number of stream segment of the river order by the number of stream segment of the next higher order. The lower bifurcation ratio are the characteristics of a structurally less disturbed watershed without any distortion. In drainage pattern, the bifurcation ratio between 3 and 5 indicate that geologic structures have not distorted the drainage pattern of the basin. Exceed value pronounced structural control encourage the development of elongate narrow drainage basin. Higher bifurcation ratio indicate a high runoff, less infiltration, and mature nature of topography, which is the result of variation in higher and lower order stream segment. These irregularities are depends on geological and lithological development of drainage basin. It was calculated by using the given formula. Next one is stream length. The length of the various stream segment can be measured order wise, and the total length as well as the mean length of each order can be computed. The mean length for the given order can be obtained by dividing the total length of the total number of the segment of the same order. The mean stream length of a channel is dimensional property and reveals the characteristics size of drainage network component and it contributing basin surface. The mean length of stream is an increasing trend with increasing in order. The length of overland flow. Horton defined as a length of flow path projected to the horizontal of non-channel flow from a point on a drainage divide to a point on a adjacent stream channel. It is the length of overland flow of water before it joins a channel. It is reverse relationship between drainage density and overland flow. This factor relates inversely to the average slope of the channel and it quite synonymous with the length of sheet flow to a large degree. The average length of overland flow is approximate half the average distance between stream channel and is therefore approximately equal to half of the reciprocal of drainage density. The analysis reveals that the length of overland flow is varying between 0.1 to 2.26 in watershed number 11 and watershed number 2 respectively. The watershed 6 to 13 has low overland flow except watershed 9 where it is more than 1. See the figure number 4. Horton noted that length of overland flow is one of the most important dependent variable affecting both the hydrologic and physiographic development of drainage basin. It is calculated by the formula wandering ratio. The ratio between main stream length along the course of this straight line distance between the two extreme outlet and farthest point in the basin boundary. While this factor broadly indicate the amount of deviation of main stream from straight line path, it does not necessarily explain the meandering of the main stream. The wandering ratio in the watershed is varying between 1.09 and 1.89 in watershed number 3 and 4 respectively. Refer the figure number 5. The low wandering ratio shows the less time of runoff and vice versa. It is calculated by the formula. The aerial aspect of drainage basin includes the drainage area, drainage density, drainage texture, basin shape, configuration, constant of channel maintenance, etc. See the table number 7.3. The drainage area is represent the area enclosed within the boundary of the watershed divide. The watershed wise analysis reveals that among 13 watersheds, the watershed 12 has lowest drainage area, that is 3,328.4 hectare, and watershed number 1 has the largest drainage area, that is 191,209.1 hectare. The drainage area is probably the single most important characteristics of hydrologic design. It reflects the volume of water in the watershed that can be generated from rainfall and the length of the stream draining it. Watershed shape factor. The watershed shape factor was defined as a ratio of the main stream length to the diameter of the circle having the same area as of watershed. See the figure number 6. The analysis reveals that the watershed shape factor is varying between 1.59 and 4.73 in watershed 12 and 3 respectively. The low value shows the high runoff and circular in shape, and high value shows low runoff and elongated shape of the watershed. It also reflects the drainage pattern of the study area. It is calculated by the formula, the drainage density. It is express the closeness of spacing of channel. It is defined as a rate of total length of channel of all order in the basin to the drainage area of the basin. It is affected by factors which control the characteristics length of the stream, like resistance to the withering, permeability of the rock formation, climate and vegetation, etc. The low value of drainage density is observed in region underlying by high resistance permeable material with vegetative cover and low relief. High drainage density is observed in the region of weak and impermeable subsurface material and sparse vegetation and mountain relief. See the figure number 7. The drainage density is calculated by using the formula. Stream frequency. Stream frequency is defined as a number of stream per unit area, as you can see in the figure number 8. There is a close relationship between stream frequency and runoff. The high stream frequency has more runoff and vice versa. You can see the formula. Constant of channel maintenance. It is defined as the ratio between the area of the drainage basin and total length of the channel expressed as square kilometer per kilometer. It is equal to the reciprocal of drainage density. This parameter indicates the number of square meter of water surface required to maintain 1 linear meter of channel. Constant of channel maintenance is inverse to the drainage density. The analysis reveals that the value of the constant of channel maintenance are varying between 0.21 and 4.51 in watershed 11 and watershed 2 respectively. See the figure number 9. It means that 0.21 and 4.51 square meter surface required maintaining 1 meter of channel in watershed 11 and 2 respectively. The higher value indicate that the channel capacity should be large enough to carry high discharge resulting from the bigger drainage area. It is calculated by the formula. Drainage texture. It is a total number of stream segment of all order per parameter of all that area. It is the coarseness or fineness of the dissection of the drainage network. The drainage texture of the watershed is varying between 0.17 and 12.01 in watershed number 9 and 7 respectively. Refer the figure number 10. The classified drainage density into 5 different texture, that is very coarse, moderate, fine and very fine. According to Smith classification method, the watershed 1, 2, 4, 5 and 9 has a very coarse, 3 and 5 has a coarse, a 4 has moderate, watershed 12 and 13 has fine, and watershed number 7 and 8 has a very fine drainage texture. Horton recognized infiltration capacity as the single important factor which influenced drainage texture and considered the drainage texture to include drainage density and stream frequency. It is calculated by the formula form factor. It is defined as the ratio of basin area to the square of basin length. The value of the form factor would always be less than 0.7854, which is for perfectly regular basin or the circular basin. In the study area, it range between 0.04 and 0.69 in watershed 3 and 12 respectively. The watershed 9 and 3 has low. The watershed 2, 4, 5, 6, 7, 10 and 13 has medium, and watershed 1, 9, 11 and 12 has high form factor. Refer the figure number 11. The analysis also reveals that the smaller the value of the form factor, more elongated will be the basin. The basin with high form factor have high peak flow of shorter duration, whereas elongated sub-watershed with low form factor have lower peak flow of longer duration. Floods flow in such elongated basin are easier to manage than those of the circular basin. The form factor is dimensional parameter and is computed by the formula circulatory ratio. Basin circulatory ratio is defined as the ratio of the basin area to the area of circle having circumferences equal to the parameter of the basin. It is influenced by the length and frequency of streams, geological structures, land use, land cover, climate, relief and slope of the basin. The basin shape approaches to the circle, the circulatory ratio approaches to 1. The circulatory ratio in the study area is ranging between 0.12 and 0.74 in watershed 1 and 12 respectively. Refer the figure number 12. It is computed as the ratio of basin area to the area of the circle having same parameter as of the basin. The higher circularity ratio also indicates the larger amount of flow and vice versa. It is calculated by the following formula. Elongated ratio. The Shum has defined as the ratio between the diameter of the circle with the same area as the basin and basin length. The value of elongated ratio approaches to 1 as the shape of the basin approaches to circle. The circular basin is more efficient in runoff discharge than elongated basin. The value of elongated ratio in the study area varies between 0.23 and 0.94 in the watershed 1 and 12 respectively. Associated with a wide variety of climate and the geology, as you can refer the figure number 13, value close to 1 are typically of region of very low relief, whereas that of 0.6 to 9 are associated with high relief and steep ground slope. High value of elongation ratio indicate mature to old stage topography. Higher value of elongation ratio have circular shape. It is calculated by the formula. The relief aspect. Basin relief. Basin relief is the maximum vertical distance from the stream mouth to the highest point on the divide. Basin relief has defined in several ways, measured it along the longest dimension of the basin parallel to the principal drainage line, whereas Stroller obtained it by determining the mean height of the entire watershed divide about the outlet. In the Son-Karamnasa interflow, basin relief is ranging between 38.44 meter and 593.96 meter in watershed number 1 and 7 respectively. Watershed 1, 2, 5 has low, 9 to 11 and 12 has a medium, and 3 to 4, 6 to 8 and 13 has high basin relief as mentioned in figure number 14. Relief is an indicative of the potential energy of a given watershed about a specified datum available to move water and sediment downslope. It is calculated as relief ratio. The ratio between basin relief and the basin length is known as basin ratio. It is normally shaped basin. The ratio is a dimensionless height minus length ratio equal to the tangent of the angle formed by the intersection of the basin mouth of a horizontal plane passing through the highest point on the divide. The relief ratio in the watershed is varying between 0.03 and 1.75 in watershed 12 and 2 respectively, as mentioned in table number 4 also. The watershed 1 and 2 has highest, watershed 5 has medium, and other has low relief ratio as figure 15 shows. This parameter permit comprises of relief of the two basin without regard to the scale of the topo sheet. It measures the overall steepness of the watershed and can be related to its hydrologic characteristics. It is calculated as area elevation relation. Distribution of area between contour in a drainage basin is of interest of comparing drainage basin and to understand the storage and flow characteristics of the basin. For the purpose, an area distribution curve can be obtained by computer system itself in between contour. The mean elevation is determined as a weighted average of elevation between adjacent contours. In the Son-Karamnasa interflow, about 73.26% area below 200 meter above mean sea level, which is almost plain. The 26.74% area is above 200 meter above mean sea level, which is very high slope as shown in figure number 16. Relative relief. It is defined as the ratio of the basin relief to the length of the parameter. Relative relief is an indicator of the general steepness of a basin from summit to mouth. The analysis reveals that the value is ranging between 0.16 and 10.97 in the watershed 1 and 12 respectively, as shown in the figure 17. It has an advantage over the relief ratio in that it is not dependent on the basin length. It is calculated by using the formula given by Melton in 1957. Ruggedness number. It is the product of the basin relief and the drainage density. It describes the quality of the slope steepness with the length. This is a dimensionless measurement and combined slope and length characteristics into one expression. The area of low relief but high drainage density are ruggedly texture as area of high relief having less dissection. It is calculated by the formula stream sonicity index. It is the ratio between the river channel length and length of river valley. It represents the degree of deviation of a stream actual path from expected theoretical straight path. The value of index indicate The river course such as Tortuous index value is 2.1, irregular that is 1.7, regular 1.5, transitional 1.2 and straight the index value is 1. The value also indicate the stage of basin development and landform evolution. It is calculated by the formula. The conclusion is the drainage basin and their morphometric parameter of different aspect like linear, aerial and the relief shows the different characteristics of the watershed. These different characteristics can be used to interpret the geologic condition responsible for, and the pattern is controlled by and in turn has an influence on the hydrology of the drainage basin. Drainage pattern refers to spatial relationship among streams or river which may be influenced in their erosion by inequalities of slope, soil, rock, resistance, structure and geologic history of a region. Linear parameters have a direct relationship with runoff and erodibility. Higher the value, more the erodibility. On the contrary, as the shape parameter have an inverse relationship, the runoff and erodibility. Lower the value, more the erodibility. More the relief value, higher the runoff and more erodibility. Basically, remote sensing and GIS has an efficient tool in drainage delineation and their morphometric analysis. These morphometric parameters can also be used for prioritization of the watershed for land and water resource development plan. Thank you.